John, who's going to talk about randomized smoothing for stochastic optimization.
Okay. What's that?
Parallels.
Oh, yeah, maybe. Yeah, sometimes my title changes. It's parallel, yeah. Is the mic working? Are we good? Good enough. Okay, yeah, thanks a lot for giving me this chance to talk. So this is joint work with my advisors or something like that, Peter and Martin. I don't think either one of them is officially my advisor. So let me start by just setting us up. So I want to solve stochastic optimization problems. I mean, I can essentially write everything I do in about 15 characters. So I want to minimize some function f of w subject to w belonging to a constraint set. And for this talk, I'm going to assume f is some expected function. So either an empirical expectation on some data set, you get a set of x's and you want to minimize the average loss over your data, or you're just getting samples from some distribution you don't know, you want to minimize that expectation. So examples we're all probably familiar with. Logistic regression, where the data is x, y pairs, y is the label, x is some feature vector. SVMs, again, data is x, y pairs, x is the features, y is the label. So these are the types of problems that I'm going to care about. So real quick review, you've probably all seen this or heard it 10 times, but so stochastic gradient descent. What we do is it's an iterative algorithm to solve our minimization problem. And how it works is that at iteration t, we receive some gradient, gt, which is random, but an expectation is the gradient of our loss, evaluated at the current parameters. Then we take some step in the negative gradient direction with some step size alpha t. And that's going to decrease over time. So simple example, if we have this empirical data set where we've got an average over our xi's, we can just choose I uniformly at random, and that's our gradient. So what does this look like? So here's the contours for a loss function. You know, we start here, we sort of take random steps, but eventually they shrink small enough and we kind of converge to the minimum of the function. So what happens when we have kind of like parallel computation? So this is something that I think everyone sort of knows we should do, which is to try to get lower variance estimates of the gradient, right? So if we start off, this is the true gradient of our function right here. So it points right down towards the middle. And we can imagine getting lots of stochastic gradient samples and averaging them. So, you know, if we have a fairly low variance estimate, it looks pretty good. They point us pretty much in the right direction. So this is when m is m, the number of samples here is something high. And as we get fewer and fewer samples, we get more and more noise, and the gradient becomes less and less indicative of where we should go, right? And eventually we sort of, I mean, they're almost random, although in expectation they point the correct direction. So it turns out there is a theoretical justification for doing this, although it's pretty recent. So the normal sort of stochastic gradient rate that we've all seen, at least for not strongly convex functions, is after t iterations of stochastic gradient, our sort of optimization error is 1 on square root t, give or take. And then in the past few years, there's been a lot of work, or there's been some work on what happens when we can sort of get reduced variance estimates of the gradients. So if we use m gradient samples and our function f is suitably smooth, then we get an error which is sort of scaling as 1 on t plus 1 on square root tm. So we've essentially got this linear improvement in the number of samples we get. But the problem here is that there's this kind of caveat, which is that we have suitably smooth functions. But there's lots of non-smooth problems we care about, right? So I think all of us like to solve SVMs. You know, they're kind of nice things to solve. Sometimes we might like to solve robust regression problems because we don't want to pay some huge error for being too far off. You know, we don't want to go as the square. We want to grow linearly in sort of our errors. Now these two, you might argue, well, I can smooth these out. You know, I can use a Huber loss, or I could use logistic regression, and they're smooth. But you know, we also care about structured prediction, where we have some loss. Say we're like trying to find parse trees, okay? And so we have some feature mapping, phi of our data x, and then some structured label y, and we want to find weights that so that sort of the maximizing y within this feature function is correct. And I defy you to find an efficiently computable smooth version of this for most problems. I mean, like, say you're trying to learn matchings. You know, this set is exponentially large. It's going to be really tough to get a CRF over the space of all matchings in a graph. Anyway, and we really care about solving these kinds of problems. So to give some intuition for why it's hard to solve non-smooth problems, or why sort of getting multiple stochastic gradients isn't really helpful, I think this picture can help. So if we get a really low variance estimate of the gradient of the absolute value up here, it's a pretty good indicator of where we should go. You know, we're here, the minimum is way far away, so we want to go fast that way. If we get a really good low variance estimate of the gradient right next to the minimum, it's going to tell us that, you know, it's going to have the same exact gradient as here. But that's totally wrong. It gives no indication of global structure. So if you had lots of parallel computation, I think sort of the natural thing to do is instead of asking over and over for the gradient at this point, let's ask for gradients or subgradients around our current point. So we start here, and then we just sort of randomly perturb the point where we ask for the gradient over and over, and then we sort of get most of the sort of observed gradients we get point this way, but enough point back this way that it sort of effectively smooths out our loss function, and we get a much better sort of picture of what the function looks like. You know, now if I ask for the gradient here, it's going to tell me don't go that fast when you go down. So we can do this in parallel if we've got lots and lots of processors. So what's the algorithm? Well, the normal. So I'm just going to try to tie this back into normal stochastic subgradient descent. So normally we have our weight vector W, and we sample some x from our distribution over x's at random, and we take the gradient and we go in that gradient direction. Now our approach is going to be to add random noise to W, so we just add some random perturbation. We take the gradient there, and we decrease the magnitude of the, we take the gradient there, take the gradient in that direction, and then we decrease the magnitude of the noise over time. So what this looks like is essentially it sort of smooths out our gradient estimates and makes them point sort of in a more correct direction, right? So we went from here to here, and then as we get closer to the optimum, we decrease the amount of noise we're adding in. And just because I would feel really bad about having a talk without actually giving the algorithm, I'm going to write it here. It's a bit complicated. If you've seen accelerated gradient methods, then it should look mostly familiar. If you haven't, then I'm sorry, I won't spend that much time giving intuition for it. But essentially what it is we have a sort of query point where we're looking for gradients, and then this exploration point, which is really aggressively trying to minimize our loss function. So what we do is we randomly perturb the point where we want the gradients. We get this average subgradient, and then we have this kind of approximation to our function. It's some sort of linear approximation, and we regularize it to make sure we don't take steps in totally awful directions. And then after we solve for this aggressive exploration point, we sort of interpolate between it and our previous points and keep going. So the nice thing is that we have actually pretty strong, well, reasonably strong theoretical results for this. So again, this is our objective. We want to minimize this expected function. So in the non-strongly convex case, where you just have, I don't know, say, an L1 regression problem with no regularization or things like that, our convergence rate is 1 on t plus 1 on square root tm, where m is the number of gradient samples we get. So if we compare back earlier, this is essentially exactly the same speed up you get in the smooth case. But now we're getting it for non-smooth losses. And in the strongly convex case, a slight extension of the previous method gives basically optimal results here. So if you're solving, say, an L2 regularized SVM, where your regularization multiplier is lambda, now your convergence rate is something exponentially decreasing plus 1 on lambda times t times the number of samples you're getting of the gradient. Okay, so this, theoretically, we're getting basically the optimal speed up. It's impossible to do any better than this for any stochastic convex problem. So just a few quick remarks on distributing. So you can basically if we have our computers in a network or even just on one processor, communication can sometimes lead to some problems, right? You have communication latencies, and if communication is expensive, what you can do is basically each of your processors, you have them compute a sort of a mini batched gradient of size m, and then after they've sort of computed these larger batches of gradients, then you average them. Then you send them to your sort of master processor, whatever. and it aggregates everything. And the idea here is that sort of you take M large enough to swamp the communication cost. And a little algebra shows that basically, as long as the communication cost isn't too big, essentially we get a linear speed up in the number of processors. Yeah, so that's basically the content of the theory here. So if you have any questions about that, you can feel free to interrupt me. But let's go into some experimental results. So first, I mean, this is just to see, like, is my theory accurate? Was I basically doing the right thing? And so I'm going to define this t of epsilon and m to be sort of the minimal iteration until I have some epsilon accuracy in my optimization problem. And what our theory predicted was roughly that until m got large enough that these two terms were about the same, I should be getting sort of linear improvements in speed. And this plot shows basically that we're correct. So the blue line is the actual number of iterations it takes to get to some epsilon accuracy as a function of the number of subgradient samples we're getting for this robust regression problem. And you can see that roughly sort of the prediction and the truth match up. Another thing in our method, so there's sort of two parameters that we have to specify when we run our method. We have to specify the amount of random perturbation, like how much noise are we going to be adding in, and we also have to specify a step size, right? So step size selection is generally fairly important in stochastic gradient algorithms. So we want to know, okay, is our algorithm robust to this? Like, if I pick too much noise to put in, am I totally screwed? And the answer is, really, you're actually pretty robust. So this is a plot. So eta is my step size here, what I choose in my step size algorithm, and then u is the amount of random noise I'm adding in. So 1 on u is some kind of measure of our estimates of properties of the problem. And so this is a plot of our optimization error after 2,000 iterations of solving this synthetic SVM problem. And what you see is, so this is a range of 10 to the minus 1 to 10 cubed. So that's 4 orders of magnitude in the step size and in the amount of smoothing we're adding. And basically, for almost this entire plot, our optimization error after 2,000 steps is less than 10 to the minus 2. And even when we're like way far off in this fat corner, we're still, you know, within 0.1 of the optimal solution. So it's really robust. You could totally mess up the amount of perturbation you're adding in, and the method is going to work just fine, which is kind of satisfying, I think. You know, unmess-upable methods are pretty nice. Okay. In some problems, there's actually not. You can actually get performance benefits without even distributing. So, for example, if we're doing projected gradient and we have to project to some complicated set, then sometimes, I mean, it may make sense just to aggregate gradients a lot before projecting. So this is an example of a metric learning problem where we're trying to learn some positive definite matrix so that we're getting points, and we want to sort of have related points be close together according to the metric we learn. And we have to project the positive semi-definite cone, which is much more expensive than computing subgradients of this objective. And so this plot just shows the actual time in seconds to learn a metric as a function of the number of gradient samples. And you can see that, you know, up to getting 128 or so samples, we basically have huge improvements in training time, even without doing any multi-threading or anything. Okay, but those were all synthetic experiments, so now I'm going to go through a couple real ones on a real, like, I think this was a 12 core machine with like 12 gigs of RAM, something like that. And so these are experiments on an SVM problem using the Reuters RCV1 data set, which is this, you're trying to classify news articles from the Reuters news service as to whether they're about economics or government or something like that. And so this plot shows the amount of time it takes until we get to different optimality gaps on our problem, until we have optimized to a certain accuracy, right? And the red line is when we use a batch size of 20 on each of our processors, right? So we had that picture. Each processor now is computing 20 gradients and then sending them in. And the blue line is with a batch size of 10. And we see that, I mean, essentially, you know, the time to actually solve this problem goes down and down and down until we get to about 6 or 8 threads. And when you actually require more a more exact solution, you still get more improvements by adding more and more threads. And this kind of matches our theory as well, that if we increase the batch size, we actually get some benefit because the communication latency doesn't hurt us quite as much. And just another view of this data set. This is a plot of the optimality gap as a function of time in seconds for using different numbers of threads. And this black line at the top is Pegasus, which is Shyashelev-Schwartz and Yoram Singer's sort of SVM algorithm, which I guess is roughly state-of-the-art for single processor solutions. And you can see that even if we're only using one processor, we actually do better than Pegasus, which was kind of surprising to me, but it's sort of a nice result that this even helps if all you have is one single processor to solve these problems. And I also have some results on learning a parsing model. So these are tests learning a hypergraph parser for using it with the Penn tree bank data set. So the goal is, you're given, so here are points X, the data, are sentences, and Y are parse trees, or hypergraph parses. And this is just and so this problem is really nice for sort of our setting because actually computing the objective at all takes a while, right? So each of these hypergraphs has something like, I can't remember off the top of my head, but tens of thousands to hundreds of thousands of edges. Like each individual hypergraph is on the order of a megabyte. So it takes a relatively long time to even compute one objective. So doing this random sampling is really helpful because we don't have to worry about communication and things quite as much. So on the left plot, I'm showing essentially the gap in the optimality of our algorithm as a function of the number of iterations for different numbers of threads, 1, 2, 3, 4, 5, 6, 7, 8, or 1, 2, 4, 6, 8. And we can see that the more threads you get, the better off you're doing. And this plot is the actual amount of time in seconds it takes to do this. And you can see they don't totally match up. Sort of at the beginning, all of the multi-threaded versions are sort of right on top of each other, and then eventually they separate. And I think this is roughly because, when you can only load part of this data set into the memory of your computer. It's about 40 or 50 gigs if you actually load the whole thing. Thanks. And so there's some memory latencies that I haven't totally figured out here, but there's still a substantial benefit to using more and more threads. And this is sort of a Pegasus type algorithm with a single thread. Yeah, so that's about it for my talk. I should acknowledge my collaborators, so Martin Wainwright and Peter Bartlett, my co-authors, and then Slav Petrov and Sasha Rush at Google helped a lot with the NLP experiments, and Yoram Singer and Mike Jordan gave some feedback to earlier versions. So thanks a lot for your attention. I have a fixed learning rate? Yes. No.
What is eta?
Eta is just the multiplier on the learning rate. I didn't really write it here. But this is yeah. There's a learning rate in there. There's one specific learning rate that you use. It's specified in the paper. So all you choose is the multiplier.
So it decrease now 1 over of t.
Yeah, it roughly decreases as 1 under t. But yeah, I didn't put it up there because the formulas get kind of messy. They're easy to implement.
Have you tried to say tried to use it to do like the swaps operation, like the last objective or the last sequence of this?
I think I have. Have I? Probably. It certainly applies to that setting. Because you can directly incorporate a regularizer. Where's the update? You can directly incorporate a regularizer into this update. It just appears here in the consultant processing. I didn't put it here because it makes the slide look even worse. Good switching. Yeah.
Thanks for a nice talk. So I'm wondering about the noise term you had. Do you think it would be worth looking at other kinds of noises and other non-Gaussian noises?
Oh yeah. Well, yeah, it seems like I understand Gaussian noise. You can use any kind of noise you want. Any kind. As long as it's a density with respect to the Lebesgue measure, they're going to basically be exactly the same.
The theory models?
Yeah. I mean, there's some weird things with dimensionality depending on like what norms you're using, but in practice, it's all the same. But yeah.
Since it's a workshop, I'm going to ask a very general question.
Yeah.
So in the old days, the days of the square root t, essentially from central limit theorems, one could show that the averaging trick and Newton methods obtained the same covariance, therefore why people started doing averaging, because theoretically they were just equivalent. But then in practice, people started showing in the finite regime some Newton methods actually can do better than averaging. Not always, but in some cases that's the case. With the new advancements that you're putting forward in terms of both theory and experiment, do you think one will be able to tease out that difference? Well, in this domain, stochastic Newton methods do better, and if they do, can we come up with rates that actually discriminate between them?
Yeah, that's a good question. I think it's going to be hard, at least in these kinds of problems, to get a Newton method because all my problems are non-smooth. So there's no gradient exactly.
There's some bound optimization that makes use of.
Yeah, I don't know. I don't have a good answer to your question. I think I would need to read more about sort of stochastic Newton things to be able to say something intelligent. Sorry. Yeah.
So actually, if we're talking about just the deterministic setting, there has been some work by Lewisburg and Overton for stochastic for gradient sampling relatively recently, a few years back.
Yeah.
And they focus on non-convex case.
Right. Was this Adrian Lewis?
Yeah, right, exactly.
Right.
And they actually use BFGS updates, which works really well even in the non-convex case, just on the gradient samples. And what I'm wondering is that, so your update seems to be, I mean, your general, you're not doing line search like they do and things like that. So if you actually apply this to deterministic setting, would that give some, different results? I mean, I'm sure it will get different results. Have somebody done it before? Would it be better?
I actually know the answer. That's the Nemirovsky beauty. Just smoothing the Gaussian convolution. I mean, you gotta go back and remember everything's the Nemirovsky beauty.
Right.
Yeah.
So they apply to
if you can actually evaluate the smoothing.
No.
Oh,
just by Gaussian smoothing.
Okay.
Because without a stochastic function.
No, you determine the function, but you take samples,
Okay.
and that smooths it. You take the
Okay, so it will be the same?
You might,
Yeah.
you may be able to do that. I mean, this is related to sort of, Nesterov had this paper in 2005 on smooth optimization of non-smooth functions or something like that, where you sort of smooth by putting the procs in and solving the procs dual.
Yeah, but I mean, you're doing it by
Yeah, right. So I think if you could sample accurately enough, you get something similar to that. But, we're never off the other solve it.
That's the answer. Let's thank our speaker.